Methane extraction. Coal bed methane extraction is one of the nation's fastest-growing alternative energy industries, currently accounting for approximately 7% of the nation's natural gas supply. Coal bed methane extraction is a process for collecting methane reserves from coal deposits. The increasing demand for alternative energy sources and cleaner burning fossil fuels will undoubtedly continue to stimulate growth in this emerging industry. Although coal bed methane is touted as clean energy, the extraction of coal bed methane has significant environmental consequences on the local ecology. At particular risk are local residents, farmers and businesses relying on ground and surface water for domestic purposes. What is coal bed methane? Coal bed methane is a natural gas byproduct of coal formation. During coal formation, organic matter is chemically broken down into simple organic compounds. Methane is a byproduct of this breakdown. Coal is very porous but lacks matrix permeability. In other words, water can seep into coal but can't flow through it. Naturally occurring fractures in coal allow groundwater to permeate the coal and provide the means through which the methane is stored in the coal bed. Due to coal's porous nature, methane gas produced during coal formation is absorbed into the coal bed and held in place by the weight of the surrounding groundwater. How is coal bed methane extracted? In order to commercially produce coal bed methane, it is necessary to decrease the water pressure within the coal bed. When the pressure is decreased, the methane gas naturally desorbs from the coal and migrates through the coal bed. This natural phenomenon is the basis for coal bed methane production. In extracting methane from coal beds, a well is drilled down to the coal bed and the sides of the well are then encased in concrete. A water pump is dropped down into the coal bed and the top of the well is sealed with a venting pipe to collect the methane. Large amounts of groundwater are pumped out of the coal bed, causing a corresponding decrease in water pressure. The decreased water pressure allows the methane to escape from the coal and migrate along the coal fractures and up into the well. The methane is then pumped from the well through the venting pipe where it is compressed and sold. What are the environmental effects of coal bed methane extraction? Water depletion. One of the environmental effects of coal bed methane extraction is the immense quantity of water pumped out of the coal bed aquifers. On average, approximately 12–15 gallons of water per minute are pumped from each well. During the initial phase of production, water is pumped at a very high rate. The extracted water is typically discharged into local streams or re-injected into the ground. Where the coal bed groundwater is relatively pure, surface discharge is the most common method of disposal. Smaller quantities are sometimes stored in large pits for evaporation, but this method is inefficient to deal with massive quantities of extracted groundwater. The removal and disposal of so much groundwater raises several concerns. One concern is that drainage of a coal bed aquifer will cause shallower aquifers to drain into the cavity created by the coal bed water extraction. This is a particular concern for local landowners relying on well water pumped from shallow aquifers, which is often the case, as aquifers used for domestic water wells tend to be shallower than coal bed aquifers. In several reported cases, local water wells have gone dry after coal bed methane operations have begun. A similar concern exists for coal bed aquifers that are tributaries to surface waters or adjacent groundwater aquifers, that is, coal bed aquifers that contribute to other water sources. The drainage of tributary coal bed aquifers can cause a corresponding decline in the water levels of the contributory water sources. Consequently, water depletion from coal bed methane operations can have a significant impact on residents, farmers and businesses relying on affected water supplies. Surface water discharge. because surface discharge is the most common disposal option for the extracted coal bed water. The compositional characteristics of coal bed water can have a tremendous impact on the surrounding ecology. The quality of coal bed water varies considerably from well to well and basin to basin, but, on average, the deeper the coal bed, the more saline the water becomes. Other compositional elements typically seen in extracted coal bed water include major cations, positively charged ions such as sodium, potassium, magnesium, and calcium. Major anions, negatively charged ions such as chlorine, sulfate, and hydrogen carbonate. Trace elements and metals, iron, manganese, barium, chromium, arsenic, selenium, and mercury. Organics, hydrocarbons and additives. The saline and sodic quality of coal bed water can have catastrophic impacts on local agriculture when discharged into local waterways. The moderate to high levels of salt in coal bed water can destroy soils and decrease crop production. The salts gather in the root base of plants, making it harder for the plants to extract water from the soil and inhibiting growth. As many farmers make use of stream and river diversion to water their crops and grazing fields, the surface discharge of coal bed water can negatively impact local agriculture. Unlike salinity, which measures the quantity of dissolved salts in water, sodic water is measured by the proportion of sodium to calcium and magnesium. Sodic water interacts with fine soils, like clay, and results in the formation of a hard crust that severely impairs water and air permeation. Sodic water can cause a sharp decrease in the growth of crops and other vegetation. Chemical and radioactive contamination. Because coal bed methane extraction depends upon the natural fractures within the coal bed, gas companies routinely attempt to increase the extent of coal bed fracturing in order to boost methane production. Hydraulic fracturing is a technique used for this purpose. Hydraulic fracturing pumps a mixture of heavy chemicals, water, sand and/or other materials down an extraction well under extremely high pressure in order to achieve the desired fracturing. Hydraulic fracturing raises serious concerns because of the chemicals being used and their impact on the local ecology. If the coal bed aquifer is tributary to surface water or other groundwater aquifers, chemical contamination can spread into domestic, agricultural, and industrial water supplies. Because hydraulic fracturing typically precedes the water extraction phase, much of the fracturing fluid will be pumped out of the aquifer along with the bulk of the groundwater. Where surface discharge is used to dispose of the extracted groundwater, the fracturing fluid is discharged along with the groundwater directly into local waterways, potentially contaminating water sources relied upon by local communities. The types of chemicals used in fracturing fluids vary from company to company. In some states, companies are not required to disclose the chemicals used in their mining operations, so the extent of contamination is still unknown. Based on material safety data sheets obtained from several coal bed methane operators, many of the chemicals used are highly toxic, water-soluble, volatile, and highly mobile. Some are even radioactive. Despite the fact that large amounts of hazardous chemicals are known to be injected directly into the coal bed aquifer, there is shockingly little oversight. Coal bed aquifers often contain potable or high-quality water, and the injection of fracturing fluids into such water sources can permanently contaminate a viable source of water. Conclusion: coal bed methane production is a rapidly growing industry that will undoubtedly continue to expand under the nation's demand for alternative energy sources. Although global climate concerns have illustrated the need for the development of clean-burning fossil fuels, coal bed methane production is not without its environmental hazards. Water depletion from coal bed methane production can adversely impact adjacent residents, farmers and businesses that rely on local groundwater and surface waters. The saline and sodic quality of coal bed water can inhibit plant growth when discharged into local waterways. Chemical contamination resulting from hydraulic fracturing poses a significant threat to domestic, agricultural, and industrial water supplies and anyone unfortunate enough to be exposed to such hazardous materials. While the use of cleaner energy sources must be encouraged, such development should not proceed to the detriment of local communities. To release methane from coal seams, the groundwater trapping the gas must be continually pumped out. The water contains a cocktail of chemicals including carcinogenic hydrocarbons such as benzene, toluene, ethyl benzene and heavy metals such as arsenic, cadmium, mercury and lead. Coal bed methane wells are hydraulically fractured to increase the flow of water and gas. Millions of liters of produced water has to be disposed of from each well. Over time this represents a massive volume of water and toxic material released into rivers, estuaries and the sea. In most cases the industry claims that the water does not require treatment or detailed monitoring, which is not true. Continuous removal of water from coal seams depletes groundwater and may eventually lower farmers' boreholes and surface water flows, streams and rivers. It can also change the flow of groundwater, drawing fresh water into the coal seams. Lowering the water table has allowed methane and other gases to be released into streams and aquifers in other countries. Large quantities of methane, hydrogen sulfide, nitrogen oxides, NOx, and other pollutants are emitted from site equipment, diesel generators and trucks. Noise pollution and further emissions of methane and airborne pollutants occur as the gas is processed and pressurized in sprawling temporary infrastructure. Flare stacks burn off unwanted gases and cause noise and light pollution and more toxic emissions. Methane migration into aquifers. The coal bed methane, CBM, process along with hydraulic fracturing releases methane from coal seams. The gas wells themselves are the most common pathway for methane migration, leakage, but once released, methane can also migrate through the overlying geology. This can lead to high levels of methane in streams, aquifers and eventually drinking water. Methane is 100x dangerous than carbon dioxide as a greenhouse gas. Leaking wells are a huge problem. 6% of gas wells leak immediately and 50% of all gas wells leak within 15 years. Exploration requires thousands of wells to be drilled. These wells can never be removed or recycled. The steel and concrete structures plunged deep into the geology decay slowly over time. All gas wells will leak eventually. Dangerous work environments. The jobs created by the fracking industry are small in number for the size of the investment. Local job creation is short-term, unskilled and in high-risk areas, occupations. These workers are at increased risk of industrial disease and accidents. Exposure to chemicals and produced water creates acute health risks for workers. The result of this type of dispersed industrial development on the countryside is catastrophic. Wildlife corridors are disrupted. Edge effects created by the cutting up of habitats into smaller and smaller pieces threaten biodiversity, and the release and distribution of toxic compounds adds to the cumulative impact. If this industry is allowed to get in, the number of communities under threat will increase massively. The impacts and dangers are acute and borne by local communities who find themselves living in gas fields. The rewards go to an elite of shareholders, directors and investors. Stopping this industry in India will send a clear message to other countries that the impacts and dangers are unacceptable. Pipelines, compressor stations and flaring are needed. A sprawling temporary gas infrastructure is needed to connect thousands of sites across the landscape. The pipelines used for transporting gas and waste create the additional danger of leaks and explosions. Pipeline construction cuts scars across the countryside and blights surrounding areas with planning restrictions. Flare stacks burn off unwanted gases on every site and cause noise, light pollution and toxic emissions. Noise pollution and further emissions of methane and airborne pollutants occur as the gas is processed and pressurized. Many wells require many sites which in turn require access roads, foundations, floodlights, CCTV and enclosures. This pattern of development divides countryside, threatens rights of way, damages and slowly destroys the natural beauty and diversity of an area. Damage to existing industries is imminent. Farming and food production, recreation and tourism suffer at all stages of coal bed methane exploration, appraisal and production. An area's reputation and land base are exposed to long-term dangers that exist even long after the industry has gone. Removing liquid and solid waste requires many tanker, truck movements for each site. This is in addition to construction vehicles and drilling and fracking equipment when the site is commissioned. Because the lifetime of each well is short, 5 years, this armada of heavy vehicles will roll across the countryside. Road damage is an inevitable consequence of methane exploration due to intensive transportation of materials and machinery. Subsidence and earthquakes may be caused by the process and are quite common in conventional coal mining. The cost of the road damage caused by fracking traffic will surpass the tax revenues generated by them. Homeowners in the extraction areas can find themselves trapped in a house they cannot sell, remortgage, insure or develop. An area already suffering from a decline in existing industries is further impacted by industrialization, sites and pipelines, air and water pollution and the resultant health impacts. Methane will not replace other fossil fuels, it will be burned in addition to the oil, coal and gas that has already been discovered. By developing these new energy extraction techniques we are expanding global reserves of hydrocarbons and increasing emissions. The chemistry of the atmosphere is changing and due to drought, flood and starvation the global death toll already stands at 450,000 annually.